So first of all, what is an electric dipole? As you can see the definition, an electric dipole is defined as a couple of opposite charges Q and minus Q, means they have same magnitude but opposite sign, separated by a distance which is usually denoted by 2L. And there is another term which is important related to electric dipole, that is electric dipole moment, and it is defined as the product of the magnitude of one of the charges constituting the dipole and the distance between them. That is, it can be represented by a symbol P vector, and P is Q into 2L, where Q is magnitude of one of the charges and 2L is the distance between the two, and it is a vector quantity. And by default, its direction, the dipole moment's direction, is always from negative Q to positive Q. Now, how a dipole looks like? This is a theoretical diagram of a dipole. This is plus Q, this is minus Q, and these are the field lines which are originating from plus Q charge and terminating at minus Q as the property of field lines. Now let us derive electric field at any axial point due to an electric dipole. For that, let's make a diagram first. This is, say, this is a dipole. The distance between the two dipole is, say, represented by 2L. This is, say, minus Q, this is plus Q, and this is the midpoint of the dipole. And let us consider a point P at any distance r from their midpoint. So say P is somewhere here, this is point P, and let's name them as A and B. And since O is the midpoint, thus this distance is L, and even this distance is L, half of 2L. Now, direction of electric field would be somewhat like this. Here it would be electric field at P due to B, and this would be representing electric field at P due to A, because electric field moves outward of the positive charge and towards the negative charge. Thus, we have made the directions of these two electric fields. Now, electric field at P due to A is given by K dash Q upon distance between A and P. So here, as you can see, distance between A and P would be this whole thing, which is basically R plus L. And same way, the distance between B and point P would be R minus L respectively, that you can see over here. Now, electric field at P due to A is K dash Q upon the distance between A and P, which is R plus L whole square. Keep this as equation 1. And same way, electric field at P due to B would be K dash Q upon the distance between P and B, which is R minus L whole square. So we'll keep this as equation 2. Now, to find out the resultant electric field at P, since both the fields are in the opposite direction, thus the magnitude of the resultant electric field at P would be subtraction of the two, and since B is closer, electric field is inversely proportional of the distance of charge from the point where the electric field is to be found. Thus, this electric field at P due to B would be greater than electric field at P due to A. So, electric field at the axial point would be given as K dash Q upon R minus L whole square minus K dash Q upon R plus L whole square. So now, let's simplify this. So we can take K dash Q outside, and ultimately we can write this as R minus L whole square minus 1 upon R plus L whole square K dash Q. Now taking LCM, cross multiplying, So we'll get r plus L whole square minus r minus L whole square here, and this is like a minus b into a plus b and whole square. So a minus b into a plus b is a square minus b squares whole square. So ultimately we get some terms like this, and here it will be k dash q, and opening the bracket we'll get r square L square plus 2 RL a plus b whole square expansion, and this is a minus b whole square expansion. So r square plus L square minus 2 RL whole divided by r square minus L square whole square. So it's like k dash q. Now when we open the bracket, r square plus L square plus 2RL minus r square minus L square plus 2RL, because minus minus becomes plus, and this is r square minus L square whole square. That way. Here we see that r square, L square get cancelled, and 2RL plus 2RL would become 4RL. So ultimately we'll get k dash q into 4RL whole upon r square minus L squares whole square. So this is electric field at any axial point, but we'll reduce it to further modification. So here we'll write 2L and then R, 2R. So ultimately we'll be left with R square minus L square whole square. Now as we know, Q into 2L is nothing but the dipole moment, as we saw earlier. So say this is equation 3. So if we put this P in equation 3 in place of 2QL, then we'll get it as the axis K dash P into 2R, which we can write as 2NR whole divided by R square minus L square whole square. This is the general expression for electric field at any axial point due to an electric dipole. Case 1, when R is much greater than L, meaning the distance of the point is very far as compared to the distance between the two charges which forms the dipole. Then what happens? Then R square minus L square is nearly equal to R square. Therefore, E axial at any axial point, it would be 2k dash P R upon R square square, and ultimately it would give 2k dash P R upon R raised to 4, which would fetch us the answer as 2k dash P, and here we will get upon R cube. So this is the final expression for electric field at any axial point due to a short dipole. When R is much greater than L, then it is a short dipole. In the questions it would be clearly mentioned if it is a short dipole or not.